Select the diene and the dienophile that should be used to synthesize the following molecule. So if we look at this terminology, diene and dienophile, what this should communicate to us is that the reaction that we are looking at is the Diels-Alder reaction. And so the Diels-Alder reaction is a reaction between a conjugated diene, one that can adopt this S-cis conformation, and a dienophile. And the dienophile needs to have at least one pi bond. And so these are the 6 carbon atoms that are required for a Diels-Alder reaction to take place. And so I'm going to number these 6 carbon atoms, keeping consistent with the numbering that we have seen in other examples. And so what happens in this reaction is that you end up forming a new 6-membered ring. So you have this concerted reaction. So this pi bond here is moving to form a new single bond between the carbons 1 and 6. It's going to shift this pi bond down in between carbons 2 and 3 and push this pi bond out to carbon 5. So we're forming another single bond between carbons 4 and 5. And so these are the 6 carbon atoms that are required for a Diels-Alder reaction. And so we're drawing this model here as a starting point. So when I look at these reactions forward, I always try to find these 6 carbon atoms in the starting material, draw this framework for the product, and then just make sure that any substituents that were attached to these 6 carbon atoms are still present in the product. And so we can do the exact same thing when we are working this backwards. So if we're given a Diels-Alder product, we want to locate these 6 carbon atoms. And so it's a good idea to look for that pi bond, and so we see it right here. And that tells us that we can label these carbons as carbon 2 and 3. And then we can continue around the ring. And so when we take this backwards, we're going to say, well, we know that we needed to have these 4 carbon atoms and these 2 carbon atoms in order to make that 6-membered ring. So I'm going to draw that basic framework that we know that we need a diene, and we know that we need a dienophile that's going to contain at least one pi bond. And so then we want to look at what we have that's attached to these carbons. So I'm going to go ahead and put the numbers on here. And having these numbers will help us to track our carbon atoms. So we can see that we don't have anything attached to carbons 2 and 3. So that means in the starting material, there was nothing attached to carbons 2 and 3. If we look at carbons 1 and 4, there is something attached to those. In fact, there is this 2 carbon atom bridge between carbons 1 and 4, right? So we see it here and here. These are the 2 carbon atoms bridging carbons 1 and 4. So that means we needed to have 2 carbon atoms bridging carbons 1 and 4. So that means it is a 6-membered ring. So I'll just highlight those 2 carbon atoms that came from here. And then, so that should be our diene. If we're looking at our dienophile, we need to have these cyano groups on carbons 5 and 6. And we should notice that these are both pointing down. And so since this is a concerted reaction, any stereochemistry we see here from carbons 5 and 6 has to have come from the starting alkene. So if they are both pointing in the same direction, whether that's down or up, it's just the fact that it's the same direction, that indicates that we started with a cis alkene. So I can draw the 2 cyano groups pointing in the same direction. So that's the cis alkene, and that's because here you're talking about these pointing in the same direction, which gives you the idea that the alkene that you started with was cis. So we can see that this is option A. And so for additional practice, all of these others will work. You could go through and draw what the product would be in each case.